Hi, this is Dane Quinn at the University of Akron. Today's lecture will focus on vector derivatives. In particular, how do you take derivatives of vectors? We know that vectors have both magnitude and direction. And as a result, a vector can change both its magnitude and its direction. Right? So again, we have a scalar magnitude and then a unit vector, which denotes the direction of the vector. Of course, these underbars indicate vectors, and the fact that the magnitude doesn't have an underbar means that it's a scalar quantity. So if I were to take the derivative of a vector, right, so time rate change of a vector quantity, then I would make use of the product rule. So it's going to be the derivative of the magnitude times the direction plus then the magnitude times the derivative of the direction. And the resulting quantity would be the derivative of the vector as a whole. Again, this is just the product rule that we learned in calculus for perhaps scalar quantities, but it works equally as well for vector quantities as well. Now, I can kind of isolate these two things. If I looked at straight line motion, right? So imagine that we have, say, a point here and a point there, and this is O, and say this is P, then if this is the vector from O to P, then the velocity of P is only in the line of the vector itself, right? So here, R of P with respect to O changes magnitude, but not direction. So in particular, this second term would be 0. Now, in contrast, if I have what we would refer to as circular motion, right, so maybe I've got a point O here, and say a point P, maybe this is on a cart, then the vector from O to P would be like so, and the velocity would be in the direction of motion of the cart. Now, in this case, the magnitude of R of P with respect to O would be constant. It's just the radius of this circle. But as the cart moves around, the direction vector, right, from O to P begins to change. Right? So here, this first term would be equal to 0, and we would only consider the contribution from this second term. So these are kind of the two pieces of general vector derivatives. Of course, vectors can change both magnitude and direction simultaneously, so there might be some combination of changing magnitude and changing direction. Now, when we talk about changing magnitude, that's pretty common because magnitude is a scalar, and we know how to take derivatives of scalar quantities. However, we need to know how to also take derivatives of directions, right? So how do we deal with change in direction? So here I have two sets of vectors. I have I and j, and I'm going to assume those are fixed in the ground, and we'll let E1 and E2, now both of these are unit vectors, right? They have little hats over them. So let them be inclined with angle theta, right? So here theta is going to be this angle with respect to I and j. As a result, I can write E1 and E2 in terms of I and j. So E1 here would be cosine of theta in the I direction plus sine of theta in the j direction. And E2, this direction, of course, this angle is also theta, would be minus sine I plus cosine of j. Again, I and j are fixed in the ground, but as theta changes, right, so maybe theta is a function of time, and theta changes as time evolves, so that E1 and E2 change directions with respect to I and j. Therefore, we can just take the derivative of these expressions, these vector coordinate transformations above. So the derivative of E1 with respect to time, well, that's going to be the derivative of cosine of theta, and remember theta is a function of t, in the I direction, plus sine of theta, and theta again is a function of t, in the j direction. So once again, we'll use the product rule and some addition formulas, and this becomes the derivative of cosine of theta with respect to time in the I direction, plus now cosine of theta times the derivative of I with respect to t. Notice this is the change in the I vector as time evolves. And here this is going to vanish, right, because I is fixed. But I'll go ahead and write it out just because. And then the second term becomes the derivative of sine of theta with respect to time in the j direction plus sine of theta of t times the derivative of j with respect to t. And again, these directions are fixed, right? So that is 0, and that is 0. I and j are fixed in the ground. They don't change, right? So their derivative is equal to 0. We'll now take the derivative of, for example, cosine with respect to time. And here we'll use the chain rule, right? So the derivative of cosine is minus sine with respect to theta. And then the derivative of theta with respect to time is just d theta dt in the I direction. And then the derivative of sine with respect to time, right? So that's going to be cosine times d theta dt in the j direction. And I'll note that this actually equals d theta dt, so I can factor this out. And then minus sine I plus cosine j, well, that was just E2. So here, the derivative of E1 with respect to time is d theta dt times E2. And likewise, if I go through and I work this whole thing out again for E2, I would find that the derivative of E2 with respect to time is just minus theta dot in the E1 direction. Here, a derivative with respect to time is often denoted with a dot, an over dot. Right, so if you see theta dot, that's the same thing as d theta dt. Just some shorthand. It makes writing these things out simpler. So here we have the derivative of E1 and the derivative of E2 from a very constructive point of view. So I went and I wrote it in terms of I and j, and then I took the derivative kind of like we would normally do. And then I put it back in terms of E1 and E2. But I can reconsider this in a more sort of geometric way using the definition of the derivative. So here I have E1 kind of written in two different positions, right? So this is E1 at time t, and this is E1 at some time, slightly ahead of that, right? So t plus delta t. So between E1 at time t and E1 at time t plus delta t, those directions change by an angle delta theta. So during this time interval, delta t, I can go and write E1 at this new time, right? So E1 here at t plus delta t. And so here, this is just a little bit of geometry. You could think about our coordinate or our direction transformations, right? So maybe you have kind of this pink triangle. And I'm going to write E1 at the new time in terms of E1 and also E2, right? So here E2 would kind of be in this direction at time t. And this becomes cosine of delta theta in the E1 direction. Again, this is E1 at the original time, plus sine of delta theta E2 at the original time. Now, what I'm really going to be interested in is the displacement, right? So here, the displacement will be this vector. Right, so that'll be delta E1 at time t. So this is the displacement from t to t plus delta t. And as a result, this becomes E at t plus delta t. It's just the difference between the position vectors E1 at these two times. And here, we can take this, substitute in, and I get cosine of delta theta minus 1 in the E1 direction, plus sine of delta theta in the E2 direction. So going back to the definition of the derivative, it's the limit as delta t goes to 0 of the displacement divided by delta t, right? So that's E1 at t plus delta t minus E1 at time t divided by delta t, or using this relationship that we obtained before, the displacement of E1 is cosine delta theta minus 1 in the E1 direction plus sine of delta theta in the E2 direction. And notice that E1 and E2 here are at the original time. So now I need to use a little bit of Taylor series. So as delta theta goes to 0, right? So for small angles, and with this limit process, delta t goes to 0, so delta theta should go to 0 as well. Then we have cosine of delta theta is equal to 1 minus delta theta squared divided by 2 plus, again, higher order terms. So these are just Taylor series expansions of cosine and sine. For the sine, I get delta theta cubed over 6, and then higher order terms. So these dots indicate higher order terms. So when I take this and I introduce it here, and I let these limit processes go through, well, this first term in the E1 direction, I'm subtracting off 1, so that piece goes away. And I get delta theta squared over 2, and then divided by delta t. Well, delta t is small, delta theta is small, but again, I'm squaring delta theta, so that becomes really small, and I essentially get 0 from that term. For this second term, sine of delta theta, well, again, that's small, delta t is small, so the ratio, that could be order 1, but this next term is really small, so that gets neglected. And I end up with delta theta divided by delta t in the E2 direction. So here, I actually recognize that this boxed term is simply d theta dt. That's the derivative of theta with respect to time. And it's in the E2 direction. So here we've recovered the same thing that we had before. Go back and look at the previous slide. The derivative of E1 with respect to time is equal to d theta dt times E2. Well, there it is again. The derivative of E1 with respect to time is equal to d theta dt in the E2 direction. I kind of like this better because it doesn't rely on me defining I and j, some directions fixed in the ground, doing some stuff with that, and then going back to E1 and E2. Everything is just kind of kept in the E1 and E2 directions here, right? So in a sense, it's more natural. I don't have to rely on some other frame of reference to do calculations. But we get the same thing either way. If you were to go through and calculate the derivative of E2 with respect to time, you get exactly the same thing. Here, there's really nothing special about E1, this direction. It's just some initial starting direction. Either way, the derivative of this vector is perpendicular to the vector itself. And if you think about circular motion that we looked at initially, RP with respect to O is in some direction, and then the velocity, which of course is the derivative of position, is going to be perpendicular to that vector for, again, circular motion, which is an example where the magnitude is fixed. Clearly, when we're talking about direction vectors, their magnitude is always 1, so obviously fixed. And again, the change in a direction is always perpendicular to the direction itself. That's actually an important idea, and it allows us to generalize these directional derivatives. And we do that using the angular velocity. So I'm going to define the angular velocity of a set of directions. So let's say E1 and E2. And here, this is going to be maybe I and J. This is a three-dimensional picture, right? So E1, E2, I, and J, those are all in a single plane, and then K comes out of that plane. So we'll define the angular velocity of E1 and E2 as omega, which is theta dot in the K direction. And again, theta is going to be the angle between I and E1 or J and E2. And oftentimes we describe this angular velocity as a spin axis and a spin direction like so, omega. So here, the angular velocity would be in the K direction as sort of indicated here. This is very much the right-hand rule. So I and J being the two base vectors, and then your thumb points in the K direction, right? E1, E2, if they're spinning according to the right-hand rule, then the angular velocity again is in the K direction. So here, theta dot is known as the angular speed. And this direction K is the spin axis. So if you have an object that's spinning, right, or a set of directions that are spinning, then you can think about that direction about which things spin as the spin axis. And it's going to be perpendicular to the plane of motion. So if you think about the E1, E2 plane. Now, how do we use this? Well, again, the change in the direction is always perpendicular. right? So we need some operation that gives us perpendicular vectors. Well, that's the cross product. So here, if you think about the derivative of E1 with respect to time, we can actually define this as omega cross E1. Remember, cross products give us directions, resultant directions, that are perpendicular to both parts, right? So since the angular velocity is perpendicular to the plane, then this result is going to be in the plane somewhere, and it's also going to be perpendicular to E1. So this becomes theta dot in the k direction cross E1. And of course, if you go back and review cross products, k cross E1 is theta dot in the E2 direction. You know, in a sense, this is the definition of the angular velocity. It's the vector that works here. So that when I take the derivative of a unit vector, the angular velocity cross that vector gives me the correct answer. Likewise, if I go and I calculate the derivative of E2, it's going to be omega cross E2. So carrying this out, theta dot k cross E2, well, go back and review cross products. K cross E2 in this case is minus E1. So this becomes theta dot in the minus E1 direction. So we can actually generalize this. The derivative of any direction vector could be E1, could be E2, could be something in between, right? Could be some other vector, you know, say here. Call it lambda. The derivative of any direction vector is omega cross that vector, where this vector is fixed in what we'll say a frame of reference with angular velocity omega. So the frame of reference here would be E1, E2, K that's spinning with angular velocity omega. And in that spinning frame, right, lambda is spinning along with it. So this tells us really how to calculate the derivative of direction vectors. Going back all the way to the beginning, we pretty much now know how to calculate the derivative of vectors. It's the change in the magnitude times the direction plus the magnitude times the change in direction, where the change in direction is given by this cross product with the angular velocity. Right? So let's look at that. So here I have a position vector r of p with respect to O. Right? So p is out here somewhere. And I'm going to identify I2 and J2 as the direction of RPO, and then the perpendicular direction, just for reference, I and J are going to be fixed in the ground, right? And we'll identify an angle theta as well as a length, a magnitude of the direction of the vector as r. So r of p with respect to O here is r, and these could be functions of time in the I2 direction. And of course, I2 could be a function of time because theta is not necessarily constant. So as a result, the velocity of p is going to be the derivative of this vector. And here O is fixed in the ground. So that'll be the derivative of r in the I2 direction. We'll use the product rule. So dr dt in the I2 direction plus r times di2 dt. And that becomes dr dt in the I2 direction plus now the angular velocity. Well, it's r times the angular velocity cross I2. And because we've defined theta as positive counterclockwise, then as theta dot increases, then I2 and J2 spin counterclockwise. So the angular velocity here is theta dot in the k direction. So a counterclockwise spin is in the k direction, which comes here out of the plane. Notice that if theta dot was negative, then omega would still be theta dot in the k direction, because theta dot would be negative, and that would be into the plane of the paper or the screen or whatever you're looking at. So therefore, we find that the velocity of P is, back up to here, r dot in the I2 direction plus r times theta dot k cross I2. So we have r dot in the I2 direction plus r theta dot k cross I2 in the J2 direction. So if we were to go back, maybe r dot in the I2 direction is, say, this component. And likewise, r theta dot in the J2 direction is that component, right? So in this case, the total velocity of P would be directed like so. Essentially, r dot I2 is changing magnitude while r theta dot in the J2 is a result of changing direction. So that's our introduction and description of vector derivatives. Ultimately, we have a position vector, p with respect to O, for example, that can change its magnitude. And again, the change in magnitude is in the original direction of the vector, right? So that's I2 in this case. And we have a component due to changing direction. And that's actually going to be perpendicular to the original direction, right? So here that was original direction was I2. This changing direction term comes into the J2 direction. And it's really proportional to how fast those directions spin, right? So that's theta dot. So that's our introduction, and we'll make use of this when we talk about the velocity equations for our kinematic mechanisms. Essentially, we will use the vector derivative of the loop closure equation to calculate the velocity equations. And that totally makes sense because velocity is the derivative of position, and the loop closure equation describes positions. So its derivative, it describes velocities. That's it. Thanks so much, and until next time, bye.